This is the second part of the formal language. Let's see what we got for today. I will start with the operations on the languages. We have learned about the formal languages, and now we want to do some operations on them. And at the end, I will show you some familiar sets that you're already familiar with them, but we will look at them through our new glasses. So from formal language point of view. You remember that formal languages are sets of strings. And since they are sets, all of the operations that we talked so far about the sets will be applicable on this formal languages as well. The simplest one is the regular set operations that we are familiar with. For example, union. If you union two language, you will get another language, which is, a regular union between them. Intersection, the same thing. Minus, the same thing. The only thing that you should keep in your mind from being confused is that if you do some operations on languages, the result will be a language. The complement of languages is exactly the same as complement of the sets. The only difference is that before we learned that if, for example, we have A and A bar is U minus A, right? Now for the languages, what is the U? Is the sigma star minus the L. So the L bar will be sigma star minus L. This is the definition, and this is the Venn diagram. So if this is a sigma star, and if this is the L, then the rest of that will be L bar. Let me take an example. This is a language, and we are asking what is L bar. We know this formula, and also we already know what is the sigma star for this alphabet, right? All possible strings that you can make with zero or more concatenation of this alphabet. So zero concatenation between the alphabet, one concatenation, two concatenation, and three concatenation, and so forth, right? So this is the sigma star. To apply this L bar, we just need to remove all of the elements of L from this guy, which is here lambda, we just cross this one, B, and so forth, right? And the result will be something like that. So the result of the L bar looks like this. Based on this knowledge, I created these exercises, which are very important exercises. So first I ask you to represent L by set builder. So I described the language, and I ask you to represent by set builder, and then I ask you to calculate the L bar. To define the reverse of the language, we need just to reverse all of the strings of the language. That would be the reverse of the language. We denote this reverse as L reverse, like this, and the definition would be this. As a set builder, we define L reverse as this set builder. L reverse has some strings, W is a variable for the strings, right? Has some strings whose reverse belongs to L. So this is the definition of the reverse of a language. Here is some examples. So if this is the language, what is its reverse? We just need to reverse all of these strings, right? The B is B, AB will be BA, this guy will be BAA, and so forth, right? So this is a simple example. Let me take another better example. Our celebrity language, A to the N, B to the N, we are asking what is the L reverse. in this case, it is very easy. In some cases, it might be a little bit harder to understand, but just in case if it was not so easy, always do this. Try to enumerate some of the members of this language. So for the 0, it will be lambda. For the 1, it will be AB, and it will be A, B, and so forth, right? And then figure out, okay, the reverse L bar will be lambda is lambda. This will be BA, this will be BBAA, and then you will, find out the pattern. It will be B to the N, A to the N, such that N greater than or equal to 0. We are talking about the operations of languages. Up to this point, we have reverse complement and now concatenation. What is concatenation of two languages? If we have L1 and L2, we define the concatenation of L1, L2. First of all, we denote it with this. Sometimes we might use the dot, which means the concatenation, but if we remove the dot is okay. And we define that with this set builder. L1 is defined over sigma 1, L2 is defined over sigma 2. So they might have two different alphabet, right? The result will be the union of those two alphabets, and the language itself will be like this. It has some strings like this, such that the X is coming from L1, Y is coming from L2. Let me show this by an example. If L1 is this over A and B, if L2 is this over A and C, then concatenation of A, B concatenate with C, A will be based on the definition. It has some XY. It means that X is coming from here and Y is coming here. So it will be concatenation between A and CA, A and CAA, and so forth, yeah? So now it's AB concatenate with these guys. So ABC, and the last one will be AB, CAA, something like that. And if we want to find out this new language, what is the alphabet of this new language, we would need to union these two guys, and the result will be A, B, C. Okay, so let me give you some notes. So as we said, the concatenation based on the sets, it looks like the Cartesian product of two sets. Yeah, instead of the order pair, now we have concatenation of two strings. The point number two is if you are concatenating the phi language with any language, from left or right, it doesn't matter, the result will be phi. And I ask you to prove this. For proving this, you need to use the L1, L2 definition. The pattern is XY such that X belongs to L1 and Y belongs to L2. You need to use this definition, and instead of, for example, here, instead of L1, you put phi. So if you put phi here, what would happen? And you need to prove that it will be phi. Phi for the concatenation, it looks like 0 for multiplication. So if you concatenate, you see this 0 and multiply by anything will be 0, right? But here we have the phi. And you remember this guy, which is a formal language, we called it lambda formal language. If you concatenate it from left or right, you will get the same language. It means that this guy is neutral for concatenation. And it looks like what for multiplication? It looks like 1. We have some properties for concatenation. I mentioned some of them here. If we concatenate L with union of two languages, the concatenation has distribution property. You can concatenate these two guys and these guys and then union, or union the languages and concatenate. It can be from the left or it can be from the right. It doesn't matter. And the same thing for intersection. There are a lot of other properties. I just mentioned 4 of them for just having a taste that concatenation is a mathematical thing. So far, you have used it inside your Java code or your high level languages code, but I just want to mention that behind of all of these stuff that you are doing in computer science, there is a mathematical theory. Another operation is exponential operator. You remember about the string? If we have one string, we can define concatenation w to the n, right? We concatenate n copies of w. For the language, we have the same thing. So we can define L to the n. So we concatenate n copies of L and we call it exponential operator. Okay, let me take an example. L is A and AB. I ask you what is the L square? L cube, you would need to concatenate one more time with this guy, which is L square. So you concatenate AAB one more time with this result. You will get L cube. But my question is, I should concatenate from here or from the left? Yes, either way is fine because L square, L is equal to L square. So I just put it on the left, but it is okay if you concatenate from the right. In general, we would say L concatenate with L to the n from left or right. We will get L to the n plus 1. Now let me take a very interesting example with this celebrity language, a to the n, b to the n. I am asking what is L square. You may pause the video and try to solve this before I give you the answer. Okay, so L, if you enumerate, we said you get lambda, AB, AA, BB, and so forth, right? And now if you concatenate it with itself, what you get? Lambda, AB, AA, BB, and blah, blah. Concatenate with lambda, AB, AA, BB, and okay, so what is the result now? You need to concatenate lambda with all of them, right? So since lambda is lambda, you will get all of these stuff here. So lambda, A, B, A, B, B, and now it's time for this guy, AB with all of these stuff. AB with lambda will be AB. AB with AB will be AB, AB. All right. AB with this guy, what do you get? A, B, A, A, B, B. What is this? And we can continue. I wanted to say up to this point that A to the N, B to the N, A to the N, B to the N, I'm sorry, is not correct. This is not a good pattern because we have something like this that it is AB, A square, B square. So these guy are 1, these guy are 2. So it should be like this, a to the m, b to the m. It's not the case that always these guys are equal. So these two guys are independent than these two guys, all right? So this would be the pattern. So I ask you concatenate one more time and create L cube. So we have some special cases. L to the 0. What is L to the 0 here? Okay, so this is lambda, and I ask you to prove that. And how about phi to the 0? This is the most interesting one. What do you think about this? So if we prove this, that is provable, right? If this is correct, which is correct, then we are saying that L to the 0. What is L here? Am I specifying L? No, L can be any language. And if this is the case, then if I replace L with the phi, it should be the same thing. Okay, so I put some exercises for you guys. I ask you just enumerate at least 5 elements. Okay, so now we have a very interesting topic here. So we have some familiar sets and we want to look at them through our new glasses. Now we have some knowledge about the formal languages. Yeah, so the objective of this section is first I will show you some familiar sets and then I will introduce a very interesting set of numbers that we call them unary numbers. Okay, look at this natural number 0, 1, 2, 3, and blah blah blah. It's an infinite. The very interesting question I want to ask here, if I ask you, can I consider this n as a formal language over this alphabet? If the alphabet is 0, 1, blah blah until 9, can I consider this natural language as a formal language? Yeah, maybe someone say, "Oh, wait a minute. This is numbers. This is not a string. What are you talking about?" What do you say? When we introduce the formal language, the formal language looks like something like this. For example, A, B, B, A, yeah? And we consider all of these as a sequence of symbols, right? And these are sequence of symbols too. We define it as a number, but in fact, they are strings. Okay, so in your Java code, when you say x is equal to 54, do you think that this is a number? No, it is a string. So Java compiler read everything as a string, and then it gives a meaning to all of this stuff. So yes, these guys are strings, and the set of natural numbers is a formal language based on our definition. And how about the binary numbers? Yeah, the same thing. So this, if we consider this as an alphabet, then this is not actually a number. This is just a, sequence of the symbols. So they are strings, and the whole this guy is a formal language. So gradually, we are going to say that there were many, many formal languages so far, and we were familiar with them, but we didn't know that they are formal language. The same thing we can say about the prime numbers. The same thing we can say about the odd and even numbers. All of these stuff, the alphabet is just 10 symbols. Now we are ready to introduce a new set. We call it unary number. So it's against binary number. So binary number, the alphabet is 0 and 1. Yeah. And unary number, the alphabet is just 1. So how can we define that? Like the cave people, 1 is 1. When you want to say 2, you have 1, 1. And 1, 1, 1 will be 3, and so forth. And the interesting thing is that this is our celebrity set of numbers. So we will be using this more than any other numbers, except the natural numbers that, yeah, we use that a lot. Anyway, so what is the set of the natural numbers equivalent to this is this. And just pay attention that there is no zero here. So unary number does not have zero. It starts with 1. Okay, and this guy is equivalent to this guy. How can we create this guy with a set builder? This is actually an exercise that you will solve. Now I want to tell you something even more interesting than this. I want to introduce the addition of unary numbers. For example, if we have 1 plus 1, 1, we get what? 1, 1, 1. Agree? If we have 1, 1 plus 1, 1, we get 1, 1, 1, 1. So, what would be the pattern here if I consider all of these as a string? What would be the pattern? It will be 1 to the n plus 1 to the m equal to what? 1 to the n plus m. Yeah, the pattern will be like this, such that n greater than or equal 1, m greater than or equal 1. This is the set builder of all of this. Can I consider all of these as a string? So this is a one string. The whole of this is one string. So if this is the case, then what is the alphabet? Alphabet. 1 plus equal. You see, even the addition is a string. We can consider it as a string. But for the unary number, it was very easy to define that. For binary and the other things, it will be much more complicated. And these strings does not belong to this language, right? So this is a precise definition of the language. For example, 1 plus 1, 1 equal to 1. The whole of this is a string, but does not belong to L, if we call this guy L. And this one either. Up to this point, everything in computer science, people, is a string. All data is a string. And since the set of all strings is called formal language, it means that everything is formal language, even the audio, even the videos. So because all of them are just, sequence of the strings, and everything will be formal language. Here I put it as an exercise. Uh, let's call it a square of unary numbers. I use this symbol for a square. Your job is to enumerate and say what strings belongs to this language and what does not. And our final word, we talked about the formal language, and we know that it's a mathematical model for all types of the languages, natural language, programming language. We will get back to this topic later, and we will see very more interesting things about the formal language. I'm gonna stop here. See you guys in the next lecture.